Now we're going to talk about hypothesis testing with means, with averages. So we'll use the variable mu instead of p, and we'll use different calculator functions, but other than that, you'll see that the setup is really the same. So our first example, our hypothesis says the new baseballs don't bounce as well as the old ones did. So to test this claim, we need information about the old baseballs and information from a sample of new baseballs. So the old baseball information says when dropped from concrete from 24 feet from above, the old baseballs bounced on average 92.84 inches. The new baseball sample information, 32 baseballs were dropped on concrete from 24 feet above. The mean bounce height was 92.3 inches, and the standard deviation of the bounce heights was 1.79 inches. So we want to know, is 92.3 significantly less than 92.84? So since the claim was that the baseballs is less, we're claiming that mu is less than what the old baseballs were, 92.84. So that's going to be our alternate hypothesis since it's a less than. So our null hypothesis is mu is equal to 92.84. So then we would need a significance level, and we're going to let alpha be 0.05. Okay. So to get the testing for means, we're going to stat, and we're going to go over to tests, and we're going to choose t-test. Okay, so you'll see, if you see that menu, you want to put it on stats above. So the mu 0, we're going to put what came from our statement. So 92.84. And then X bar is going to be what came from the survey of the new baseballs. So mu 0 is the new baseballs. The mean was mu 0 is what's coming from our null and our alternate hypothesis. So that's going to be 92.84 like we already put in. X bar is what's coming from the sample. So that's going to be the 92.30, and the standard deviation was 1.79. And N, we had 32 baseballs dropped, and we want to show that this is less than. So we're going to put that information in. We're going to choose the less than, and then we're going to hit calculate. So we're going to record on the next page. So T here is our test statistic. Again, we're not going to use this because we're using the p-value method, but it's what is used to find P. Okay. So P, our p-value here is 0.049. The critical values actually are, these come from a table, so don't worry about this. If it comes up, let your instructor know and they can take that off. So since P, so remember our alpha was 0.05. Since P is less than alpha, we reject the null hypothesis. But our original claim was the alternate. So since we reject the null, that's when we support the alternate. So we support the claim that the new balls do not bounce as well as the old ones did. So we're going to do another example here. So our other claim is that male symphony conductors live longer than the average male in the general population. So in the general population, the average span of males is 69.5 years. So we're saying that our claim is that symphony conductors live longer than that their average life is greater than 69.5. So our null would be mu equals 69.5. So a sample of 35 random male symphony conductors has a mean of 73.4 years and a standard deviation of 9.7 years. And we're going to let alpha be 0.01. So we're going to fill in here. So our mu here is 69.5. Our x bar is what comes from the sample, so 73.4. Our standard deviation is 9.7. And our n is how many were sampled, 35. And we want to show that it's greater than. So you're going to go to stat, go over to tests, and we're going to go to t-test. So our mu0 here was 69.5. Our x bar was 73.4. Our standard deviation was 9.7. And there were 35 in the sample. And we're testing that it's greater. So here our t would be 2.37. And our p would be, oops, our p again, 0.012. So our alpha here was 0.01. So this number is smaller than alpha. So since p is smaller than alpha, we reject the null hypothesis. Our claim was the alternate hypothesis. So we will actually support the claim that male symphony conductors live longer than the average male. We're going to look at one more example, and this is to show you how you can take data and put it right into your calculator. So we're going to claim that the mean weight of the bumblebee bat is 1.8 ounces. So this is an equal to statement, so we'll have mu is equal to 1.8. And so our alternate will be mu does not equal 1.8. Now, since we're given the actual data of 15 bumblebee bats, we're going to put that in just like you used to for the mean and everything. We're going to go to stat edit, and we're going to put in L1, we're going to put those numbers in. So I'm going to pause the video while I put those in so that you don't have to. Okay, so you can see I put all of those numbers into L1. Okay, we're still going to go to t-test just like we have. So we're going to go to tests, choose number 2 here. Instead of stats, this is where we're going to change it to data. We put that data in. Then we're going to need, the only thing we're going to need to put in and what was our claim, so the 1.8. We're going to keep that L1 because that's where we put the data in, and we're going to leave the frequency 1. And we were testing, it does not equal 2, so we'll hit calculate. And so here we had 1.8. We're going to leave this as L1 and 1. We had the does not equal to. So our test statistic is negative 1.30 if we round to 2 decimal places. Our P is 0.216. And I don't know if we were given an alpha. So let's just use an alpha of 0.10. And this is greater than alpha. So we're going to not reject the null hypothesis. Now, since the original claim was H1, or sorry, H0. Since we did not reject H0, we'll not reject the claim. Okay, so that was an example where we're given the data, you put it into L1, and then still use that same calculator command.